So hello everyone. So I'm back with the fifth session of our course, and we are going to discuss. Um, so we'll be completing what is our diffusion model today, and we'll be laying a foundation for a class of models called core-based modeling, which will be useful in energy-based functions. So or energy-based models. So what we'll do is we'll be seeing an alternative to understanding diffusion models, and then next we'll be extending that idea to other models such as EBMs or energy-based models, and we'll see that this idea is very, very useful in especially doing conditional generation. That is, if you tell the model, please give me an image of a cat, it will only give you an image of a cat, and so on. So we'll also see, and finally, once we are done with all these, I hope that you'll have enough experience to actually build a VAE with conditioning. So that will be just a couple of few minutes of work, because conditioning, as we will be seeing, is just a conditional probability at the end of the day when you're trying to tell the model to give me a particular class of object. So that we'll get into. And before that, we'll be revising what is diffusion model. And in the next session, what we'll do is we'll be showing an implementation of the diffusion model and show its quality of generation and so on, and how it works. So let's see what the score matching based diffusion models are, and then what is conditional diffusion models, and what is conditional generation in VAEs and so on. So as we recall from last time, that in diffusion model, you have an image or any data that you have, and you keep adding noise. And then you end up getting and over steps, over t tends to infinity, a t is very large, and you get normal 0, 1 distribution. And the diffusion model is essentially a denoiser. Model is a denoiser that takes a noisy sample from normal 0, 1, denoises it, and generates a novel sample. Right? So this is what a diffusion model does. So at every step, as we saw last time, it will try to denoise it. And we have represented that using this P theta model, which we show that was a denoiser. And it was we showed that it was a model that could denoise any noise that given at any step from 0 to t. So from t ranging from 1 to t, it takes in a noisy estimate and gives your output, and gives up the noise epsilon added. This is your epsilon theta. Is what was the epsilon theta's work, was to give you the noise that was added so that you can remove it from the data. Okay, so let's see what you are doing here. Just give me a moment. Yeah, sorry for the delay. And so we were seeing that the diffusion model, what it does is, so during the forward process, we keep adding noise in this form where we get xt from the data by this generative algorithm. So this is your image, and this is your noisy image, and this is the noise from 0, 1. So we say that we're going to add small amounts of noise. We'll scale the noise because this is tending to 1. So the noise that will be added was going to be very, very small, but over infinite steps, it would actually converge, as we have shown last time, to a normal 0-1 distribution. So this is what we see, the forward process or the latent generation process. These are all latents. This process is a fixed process. It's a Markov chain, which we do not learn at all. We say that it is going to be fixed, and all we are going to learn is, since we're getting normal 0-1 at the end, we'll be learning a denoiser that will take the normal 0-1 distribution and keep coming backwards to give you x0, which is the image distribution. That's our goal. So we have seen that, and we have seen that this, again, reiterating, is that this model is essentially training this denoiser model, which could be a unit, could be a transformer. Units are, as we showed last time, they would be like VAEs, where they will be passing it through a bottleneck. And this bottleneck, we will be expanding to get back the original dimension of the data. If it is a 2D image, you could use 2D convolutions and so on. And you can look at the specific architecture in the unit paper, which was used for segmentation. So why do we use a unit or a transformer? Because as we recall from last time, dimension of epsilon is the same, or the dimension of noise is the same as dimension of x. So we are saying that latent dimension, which means that latent dimension would be the same, as the image dimension. So this is another thing to remember. So you pass it through a bottleneck and reconstruct the image back. So, or whatever you want to, and the model learns through back propagation that it has to reconstruct the noise and not the image. So here is the loss function, which is just the MSE loss. And we see that whatever noise that was added, this noise that I have over here, you try to get that out. So you pass this noisy XT through the image. You pass it through the image, and you end up predicting the noise. So this is the noise. And you end up predicting the noise. And once you're able to predict it, what we have shown is that the generation is given by the inference process is given by this equation, where we see that we have the noisy, we have this noisy image. We have the estimated noise that was added, and you are removing it. Okay, so that's what we are going to see. And then we add a diversity term here, which brings in stochasticity in the generation process, or novelty in the generation process. Okay, and then this is primarily because we say that we are going to model p theta of xt minus 1 as xt, given xt as the normal distribution, where we're going to predict only the mean of the data, and the standard deviation is going to be fixed. Right? So this is all we have seen from last time. So now one of the things that we did not observe is that I told you that at the end of the day, the model is a function of time as well as the data. So what we'll have to do is we have to make the model predict the noise for every time point, and that makes it difficult. How will the noise? So the difficulty is, how will the model know which time point t from 0. So spending more amount of time in trying to build the intuition is because the math is just algebra at the end of the day, and a little bit of probability, but we need to take away these messages that we have, that these are tricks that it will not only use in diffusion models, but also in transformers at the end of the day. So t equal to 1, 2, and so on till capital T. How would it know? How would the model know which time point to decode? How will it know? And therefore, there comes this idea. So there are two options. One, train t different models. And this is the naive option. But this is infeasible and will perform worse and will perform badly due to lack of data. So we want the same model to generalize. So if you want the same model to generalize, what you can do is you can have image features. Say you have f theta of xt. These are image features. And you give the model some features, say your E capital ET of, which is the embedding of time of the time. This is the embedding or features of time. So if you've done NLP and so on, there are three options. So you can, I'll come back to this. There are three options of doing this. Two of them is very simple. You can have fixed encoding. You could just pass the model with 0, 1, 2, and all the way to T, right? This is one of the options that you can do. And this is generally not favored because each of these positions, they're not given, so there's not a lot of a similarity of closeness between two numbers. So often when you pass a set of ones, a set of twos, a deep network would just treat them as categories. So here the problem is lack of, you may be giving one hot encoding for this, one hot encoding, lack of order with one hot encoding. That is, the temporal order is missing. The other way to do it is learn these embeddings. You can do the same. You could pass these one hot encodings for t equal to 1, and you could have t equal to 2 and t equal to capital T. You could do that, right? But what you will do, end up doing is you could have an embedding matrix, which you learn. That is E1, E2, dot, 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 ET. Again, there's this, it is difficult to learn. So what you do is, this is the embedding matrix. So whenever you do forward propagation, you get the features of time or ET of t as, say, you take the tth position, say you get this, let's put just t here. So you'll just take E into t. You're embedding matrix into time. So if you just see the second column over here, you would end up getting the second column here. And that's what you'll be learning. So this is called time embeddings, or it's used in NLP throughout, where you have this T cross T matrix, or this matrix here is a T cross T one hot encoding matrix, which you will be sampling from. So if you have the tth data point, you'll take the tth column of this matrix and you'll multiply it with a D cross T matrix, where the D is the dimension of the main dimension of embedding. So I hope you know this already. This is just an architectural tweak, and when you to extract a column out of a matrix, you just multiply with the one hot vector corresponding to this column, right? So, and you say that this is the forward propagation, right? So I'll just, what I'll do now is I'll show you the other option that you have. So before I'll go into today's main topics, so the other option is sinusoidal embeddings. Sinusoidal embeddings. So it solves two problems. One, brings in order, in temporal order, temporal structure or order. Number two, it stops us or prevents, avoids learning cumbersome, unnecessary embedding weights. Since features over time are not, or learned features over time, learned features over time are not that important, are not important to be learned. important to be learned. So all we want is some order. So instead, you could hand engineer the features, is the idea. You don't need the model to learn it. And how would you hand engineer the features is what I'll show you now. So what is typically done in the field is, say I'll show you with an example. This is just a cartoon. Don't follow it to the end. So say I have these two waves, right? This wave is a cos, say omega 0 t is one of the waves. And you have, see, this is say 0 and this is 1. This is your sine omega t, so omega 0 t, and then you have this wave over here, right? So this is your cos omega 1 t. So the idea here is, so I would like you to keep this figure in mind, is you sample at say t equal to 1, and you get these two as features from both this cos function and this sine function. Say, and then t equal to 2, you get this and this feature. So what you'll get is you'll get a set of unique combination which will represent the data. You'll have order in the data, and you'll also not have to learn the data. And it is also readily generalizable to longer sequences, which is what makes it very important in transformers. Not is not really important here. So I'll just, when I teach transformers, I'll just say that just pass a sinusoidal embedding, which means that you're doing this, right? Say t equal to 3 and t equal to 4. So these would form the features, and t equal to 6 is t. Right? So these are how I'll get the features. So what is actually done in this field is, say I want a d-dimensional embedding. Right? So if I want a d-dimensional embedding, first and foremost, or let us take 2D dimensional embedding. It has to be even because I want both cos and sine functions so that I can even match phase shifts and so on. So if I want a 2D dimensional embedding, so I would say that I would need, or we need, say d frequencies and two phases. That's the idea. Two phases is cos and sine, and d frequencies, it's what the the attention is all you need paper showed, Vaswani et al., is you often end up choosing omega as 1 by, I'll just put for the time period, I by d, where t is 10,000. This is an arbitrary choice taken because you want the time, you generally want this variabilities to be small enough. And I'll show you why this is important. So your embeddings of time for t would be these matrices. So sine, this is the collection of these omega, or you can write this as I t by t to the power I by d, and cos of t by t to the power I by d. Right? And I will have a collection of all of these frequencies from 1 to d, right? So what I'll do is, look at the frequencies once for once. So if say the I is equal to 0, right? And this I could range from, I is not generally 0, but let's take an example where I is 0. So I ranges from 1 dot 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 to I equal to d, right? So this is what it extends to. But let us take, for the simplicity purposes, say where D is large, I by D goes to 0, right? So T goes to 1. So T, or 10 to the power 0, 10 is a finite number, or 0 goes to 1. So you look at these values. So these end up becoming sine t and cos t, right? Sine t and cos t. So these you would see would not, so these have range of t ranging from 0 to 2 pi, right? So this is our time period. Time period of this waves of these embeddings, time period is 0 to 2 pi. So similarly, if I take t, I equal to 1000 or d, so what would I end up having? I would end up having sine of t by capital T, because d by d is equal to 1. And I would have cos of t by capital T. Now t is as large as 10,000, right? So what would it mean? It would mean that your time period here is going to be 2 pi capital T, right? So this is your time period. 2 pi capital T, 0 to 2 pi capital T is where this would fluctuate between. And now you can clearly see this is 2 pi to the power 2 pi into 10,000. And this is over very, very long sequences is where the time period will complete. So what I'm trying to say is T, from when T is small, you would end up having high frequencies. That is, will capture local similarities or local positional similarities. Right? So you can clearly understand, right? If your frequencies are very, very high, your high frequencies over here, so you would end up having, what do you see or what do you observe? So these are, you'll see what I'll just show you where frequencies are high. So these are, let's see what's the implication of having high frequencies. I'm not very sure what it is going to be. We'll just figure that out. So T, but we are able to understand this when T is high, or rather, let us say when I is small, that is the lower dimension in the embedding space, lower dim in embedding space. And this is higher dimensions in embedding space. So these are low frequencies. Well, as you have low frequencies, these represent something like this. So you'll have, you'll have something like this. So you'll have one graph like this. This is say I equal to D, and the other one would be something like this. And I'm plotting both the signs over here and say this is I equal to 0. So what you're observing is, so this wave that you have, right, which is the low frequency wave is unique over the entire time trajectory, right? So it will capture long-term dependencies, right? But this wave is unique only in short durations. So captures short-term dependencies. So now there's one more final icing on the cake for when you do this, and it will give you this feel-good factor. You'll just say, wow, this also happens. So we have seen that the higher frequencies as we go into the higher dimensions, so I equal to 0 and all the way to I equal to D, we are seeing these are going to include low frequencies, longer sequences, and these would show me high frequencies, shorter sequences. This is what I have shown in the embedding space. So now what I'm going to tell you is that there's one more feel good factor about it. So you see that this is T by the omega that you have, the list of omegas, say omega I, is 1 by T to the power of I by D, right? So what you observe here is T to the power of I by D. What can you make an inference from it? What inference can you make out of it? You can say that this is, see, as the powers go on increasing, so 1 by D, so if you take the log space in the logarithm space, so if I take the log of omega I, this will become minus of log of T to the power I by D. This is I by D into log of T, right? Which is a constant. This is minus of this, right? So in the log space, it is linear. So it says that in log space, it is linear. Which means if it is linear in the log space, right? If something is linear in the log space, so if f of x or log of fx is some c into x, then we clearly know fx is e to the power of cx, isn't it? We know that. So we are going to say that this is in the, and if you have it's minus cx, it's going to be minus of this. So what I'm trying to say is this frequencies that I have over here, the angular frequencies, are linear in the log space and therefore they are exponential. They are exponential. Therefore, they are exponential. What do I mean by exponential? Is that if it's a negative of this, so your omegas would be, so in the beginning, they would be very, very high and they would be quickly dropping off like this, right? So it's a, so as your I is going to be increasing, so let us write this down. So omega I is e to the power minus I by D into some constant C. So let us write this as C, right? So as your I's increase, right, when I is 0, this is 1, omega is 1. This is your omega, and this is your I. So this is 1, and this is, and when I goes from 1 to D, right, when it is D, it is e to the power minus log C, right? When I equal to D, omega D is equal to e to the power minus C, right? So e to the power minus C, say is some constant, right? So this is say e to the power minus C. E to the power minus C. So say I equal to 0, right? Then I equal to 1. Since it is exponential, it is all going to be very, very closely linked to one another. So we can show this like this. So I equal to 0 and then 1. I equal to 2. I equal to 3. So most of the things, most of the i's would be clustered over here. We know that the exponential families would have that characteristics, right? Most of the i's or e to the power minus I by d, or most of the omegas would be close to 1. If exponent is linearly changed. Right. So you can clearly see, and then you will have them spaced out because it's linear in the logarithm space. Say it's t, and then you have equal to t, and then you may have very, very spaced out things. You can show that is your homework. Plot the log spectrum or omega i's in this omega i's as a function of I. So you could do it on using matplotlib and so on. You can see that whatever I sketched here manually will be also matching there. So what I now showed is you have much more resource allocation for lower frequencies, or rather higher frequencies, than higher frequencies. What does this mean? It means that we are allocating, especially in NLP, more resources to local interference or local associations in text, in temporal space. Right? So when you have a sentence, say you have word 1, word 2, word 3, and so on, word capital T. We are interested in short-term dependencies more. Short-term dependencies are allocated more resources. Right? So this is very, very intuitive because we want only, so long term is more abstract. So what's the story, where's the state of the story, but the grammar and everything is in the short term. So therefore, if that should be perfect. And in the long term, you have this entire idea, which is abstract and is in this latent space, which does not need so much of resources. So that's one of the reasons why is this exponential or linear in the log scale set of frequencies being used to model time embeddings and sinusoidal embeddings. Okay, so we have understood this very, very like state of the art and also very, very popular idea of giving embedding. So any paper you see now, if it has positions or times as a temporal link, it will always give you sinusoidal embeddings because they're very, very, they're known to work very well, and they solve this problem. You could make this dimension of the embedding as large as possible without putting in any embedding or learnable parameters. And this actually really makes the model appreciate the dependencies between temporal between time. So we have now understood that the unit, say you may ask me where should I append this ET? You could do it at every step in the unit. So you could tell that I'm going to add it in the first layer, in the second layer, and the third layer. This is completely your design mechanism. And inadvertently, as you have more experience, you'll be seeing that once you have enough data and the model is powerful enough, the architecture really does not matter that much. You just have to have something that really works or is work is efficient enough for a particular domain. But if you have a decent model, it'll work, and you could pass the embeddings at every layer and concatenate it and so on. Right? So now we have understood the architecture, how we generate by adding noise, and how the model denoises, gives you the noise, and which you use in turn to make this generation process that we have discussed over here. So now, till now, what we have been looking at is using likelihoods. I'll be shifting gears slightly now. and we have been using this idea of likelihood where Z was giving you the data, and we were learning the variational distribution. This is what we have been doing, variational distribution to make, and we were optimizing for the elbow. So we were using an encoder, which was giving me the variational distribution, be it a fixed encoder, which a fixed Markov chain that was used in the diffusion model, or an encoder that will give you latent representations in a VAE. We were always doing an encoding process, and a decoding process was taking that encoder's output, the latent representations, be it a noisy estimate in a diffusion model or the latent dimension representation in a VAE. It would give you back the original data, which was some in one case, which was going if it was doing denoising. On the other case, it was just giving you reconstruction, which is very similar to denoising again, but in a different representation space. So what I'll now do is we need not always look into the elbow is what my claim is. Instead, the score often gives you a better or easier way to model things. So score, if you have a likelihood of log p theta, log likelihood of log p theta, the score is often defined as the gradient of the log likelihood with respect to the data. It's the gradient with respect to the data. So this is of the dimension. You will agree that likelihood is a real number. And when you take the derivative of a real number with a vector, you get the, so this is dxt log p theta of xt. So it's a scalar, and you take the gradient with with all the components from I equal to 1 to dimension of data. Say we write this as capital D. So you will get a RD dimensional vector over here. So whatever was your input, what was your likelihood, you'll get a vector which is represented as a score along what dimension, what is the gradient of the data. Often we tell this to be the saliency maps and so on. So the score is very important. It gives you an understanding of along which region. So this will give you. So if I change, so I'll just put a star over here. If I change dimension I, does likelihood increase or not, or decrease, or neither? So it tells you which of the dimensions are capturing more of the information in the data. For example, you could say that some of the dimensions, if you increase in a particular vicinity, that data does not actually reside there. For example, if you have a data from here, so if I have an xt over here, so if I take the gradient with respect to the xt, so it will tell you that the score is going to increase if you decrease xt or x, and score will increase. Here score will decrease. Your score will decrease, or your likelihood increase. So, and your likelihood will decrease. This is your p theta of x, and this is your x. So at this point, it is much likely to go towards the mean, which is more likely, and therefore it will tell you, it will give you a negative score, because the gradient will tell you go towards the decrease x, and then your likelihood is going to increase. And it is if you're going to increase x, it's going to decrease. So you can clearly see this is the likelihood function, which is going to decrease if I go towards the right. It's going to decrease. If I go to the left, it's going to increase slightly. And it could be non-linear. You could at one point it could decrease, one point it could increase, right? So this is why score is important. In a very high dimensional space, it will tell you exactly what the combination of the features would give you maximum likelihood, right? So, and often that is also used to train models. So let us now take a detour and and try to learn some probability, which we have not done in the previous lectures or previous courses. And this is going to be a little bit of an interesting thing to do. It is known that if you have a function f, and your f is trying to map from x to y, say a linear regression line like this, A simple example is linear regression line. And it's trying to make a prediction of a label y, where x is this and your y is the label, x is the features, y are the labels, right? So if you're trying to do that, so it is known in our probability and statistics that the optimal function, the optimal function is the conditional expectation. That is, you're given x, what is the value of y? Given x, what is expected value of y, of the label? So this is just the conditional expectation. The optimal function is the conditional expectation. Right? So now how do we show that? We'll prove it now. So now whenever I'm writing this expected value, the loss of the loss that I have, which is a function of f, is the expected value over x and y. That's called the joint distribution of x and y. And the mean square error, right? So let us take a 1D case where y is in real numbers. Y is real. So let's take for 1D, and if you could generalize it across ND for ND. So for 1D, if y is a real number, you could write simply f of x, and r could be in any dimension, x could be in any dimension. So f takes a real number in d-dimensional space and converts it into a real value. For example, your housing prices, number of rooms, location, and square feet, and so on. All of them would be converted into one price value, which is a real number, right? So this is your loss function. So what I'll do is, now I'll write down the expectation. So this is x comma y, p of x, y, f of x minus y whole square dx dy. So as soon as I do that, I will make a trick. I'll do a trick. I'll write a conditional expectation, p of y given x. So this is what I want generally. And f of x minus y. What given x, what is the value of y can you expect is the interpretation. And you can write this as p of x, x dx, right? I wrote dy, sorry. Yeah, so this you can write this as a iterated expectation, the expected value over x and this conditional expectation of f of x minus y squared given x. And you take a iterated expectation. So this is, we know this is iterated expectation. So now we have to show that f star of x is equal to the conditional expectation. So now we know, let us look at this. Look at expected value of f of x minus y squared given x. So the claim is, it is known, rather it's not a claim, it is known that expectation is monotonic. That is, if expectation is monotonic, it means if the inner expectation, if the inner function, rather let us write this as a function of f of x or a capital F of x, right? If capital F of x equal to this, because we know conditional expectation would give you a value with respect to a function, with respect to this random variable x. So conditional expectation is a random variable of the variable you're conditioning on, right? So you change x, you say you fix x equal to small x, and you get a value of f of x. So this becomes a function of that random variable, right? So if it is known that the expectation is monotonic, right? If the expectation is, as the expectation is monotonic, it is known if the inner function or conditional expectation is minimized for all x, the outer expectation, that the overall then what is L of f is also minimized. It's very easy to show, right? So that this, if you write this as P of x, fx dx is your LF, and we know f of x, and it is being minimized than f star of x, right? Then we can clearly this is for all x, so this is clearly a less than sign for P of x, f star of x for all f. So this is my optimal function. This is your L star. So for all f, sorry, not for all x, for a given x, for all f and all x, if it is true that your fx is f star x is the best compared, the optimal f star is always less than f of x for that corresponding data point. So this is clearly valid because it's a sum of positive numbers, and if you have one value to be always less, that is going to always give you a lower value. That is very clear. That's what I showed. So this even this monotonic property is what I proved. So now let us try to minimize this inner function. So f of x is expected value of f of x minus y whole square given x. Right. So now, for the sake of simplicity, let us take v equal to f of x. Right. So now we can say that this will become e of v minus y whole square given x. Right. So this is some function of v, say g of v. And now if I'm trying to optimize for v. So dv. So you take the partial derivative and set it to 0. dg dv, and you get the expected value of 2 times v minus y given x, right? This is equal to, so, and you set this to 0, so you get expected value of v given x equal to expected value of y given x, which means v is f star of x, v star of x, this is v star of x, right? And then what do I get? So this is your expected value of f star of x given x is equal to expected value of y given x. Now you can see this is x is already given to you, so this is a constant. And since it's already known, so your f star of x is equal to the expected value of y given x. So now we can clearly see that the optimal function for any time you have a conditional expectation is given by the condition. Anytime you have a root mean square error is the conditional expectation. So it's often very, very important. So for example, we have this in our loss function as well. We have this value, right? So we have this expectations over, we have an RMSE square, root mean square error, or a mean square error between a function that predicts the noise and the noise that was given. So the optimal function that you were going to have is the expected value of this function given the noise that was added, right? This is why. So the optimal function is the expected value of epsilon given xt is what you will have, right? So this is exactly what we are going to have, because this is the function, this is your x and this is your y. And your f star or epsilon star of xt is going to be this. Isn't it? Because this is the expected value of epsilon. That is the optimal value given xt. That is very, very nice to see, which means that if you get so it's very, again, interpretable in a manner that if you get the noisy version, what is the expected noise that was added? And that is exactly what you're going to remove, right? So again, if you're not following, what we proved now is the expected value of y given x is the optimal function for the loss function, loss of f equal to fx minus y squared, right? So this is the optimal function is what we proved, right? So we have our loss function is an expectation over this is the epsilon cap of xt comma t minus epsilon L2 norm, right? So now what I can tell you is clearly from this is the value that the epsilon star of xt is nothing but the expected value of epsilon given xt, which means given noisy data, what is the expected value of the noise added. So clearly your model is trying to estimate this term, and this is exactly what I want. So this is going to proves that diffusion models are denoisers. Because you're exactly when you train the model, it's going to give you the exact noise that was added without any stochasticity there because it's an expectation. Anyways, so now we have shown this thing that the optimal function is the conditional expectation. The second lemma that I want to show you is this. So we have been able to find out the conditional expectation. We are able to see that the conditional expectation is often very, very important because it gives you the optimal function when you're given two values, right? So now here, there's this Tweedy's formula is what I'm going to prove. It's another detour. Say x is sampled from, or x is equal to y plus n, right? Where n is sampled from a normal 0 sigma square distribution, right? And we can clearly see that the expected value of x given y is the expected value of y plus the expected value of n. And y is given to me. So this term goes to 0 clearly because it's independent and this term is y. And since you're adding a constant and you're adding a constant to a normal distribution, it stays a normal distribution. So clearly x given y is distributed as which means x given y is distributed as x y sigma squared. This is clear from our previous explanation that the mean is given and you're adding a mean to the sum of two independent normal distributions is going to be a normal at the end of the day. And you're adding just shifting a normal at the end of the day, which is going to be a normal again. This is just a shift. So it's like anything that was here would be shifted y units. This is normal y comma sigma squared. Very nice. So now I want to show you this expectation is very easy to find, right? Expected value of x given y. But what about the expected value of y given x? So this is where we could use the Bayes rule and find out the values, but often p of y given x is not known due to sampling because y is often sampled and things like that and so on. Often this is not going to be known. So we want an estimate for it in some form. So let us see how we can get that estimate. So right, so we want a useful estimate in form of since the theory. So till now I've been talking about scores. So we want an estimate in terms of scores. And any estimate, let's look at this, how we're going to get it. So let's look at this. So what I'll do is I'll just copy this and there's no space over here. There's some space. Okay, there is. So let's just look at this now. The Tweedy's formula. Tweedy's formula states that so y x is equal to y plus n. So x given y is distributed as normal y sigma squared, where n is distributed as normal 0 sigma squared. So now let us look at how we can find out the expected value of x first. Now the distribution of x, say p of x, right? So the p of x can be written as the integral of p of x given y dy dy, right? So I'll just write it in this form, x given y, p of y dy. So clearly, by law of total probability, I can write this, right? So now what I'll do is, see, this integral is over y, isn't it? So I can take a derivative with respect to x, right? If I take a derivative with respect to x, or gradient with respect to x, what I'll be ending up getting is, so let's take a gradient with respect to x, right? So for the time being, let's just do it in 1D. I think it's not a problem to do it in 1D. So we can just go ahead and do it. 1D or 2D doesn't really matter. You just take a gradient of x. If it is a gradient of x, when we pass it into the integral, it becomes a partial derivative. So it will become ddx. Even if it is a vector, it doesn't really matter. Here, p of y dy, right? So now, next is for the time being, I'll just write down the 1D Gaussian. I will write just the 1D Gaussian for derivation. It will extend to be the same for ND. Right? So let us write this down. So P of x given y is already known to us, right? So because I have already taken this to be normal, like a 1D Gaussian, so I'm not going to just not increase the length of the arithmetic here. So this is going to be 1 by 2 pi sigma e to the power of minus x minus y squared by 2 sigma squared. This is my 1D Gaussian. And then I have p of y dy. This is ddx. I'll take a derivative. So because I took the gradient inside the integral, it will just be a partial derivative with respect to x because the integral is over y. So now clearly this will become x minus y by sigma squared, right? Into, and this term is going to remain because it's an exponent and the exponent is going to remain. So I'll write this as p of x given y again and p of y dy. So I just took chain rule and I took a derivative of this exponent, and the exponent's derivative is just here. And once you have an exponent function, the exponent function already remains because the derivative of exponent is the same. So over y. So this is going to be x p of x given y dy. Dy is integral is over y minus or sigma squared gradient of x p of x, right, minus y p of x given y dy, right? Now you can clearly see that this becomes this integral. This is p of x comma y, and this is independent of y. You can just pull it out. So what you end up getting is p of x. Sorry, just a moment. So you're going to get is x p of just a moment. Let me just think about it. That's y given x into p of x. Yeah, that is correct. So I can remove x because it's an integral over y, and you will have p of xy dy minus the integral of, I'm just using base rule now. This I can write this as p of y given x into px dy, right? Again, px is not dependent on the terms, and this will also become px. So this becomes x px minus px into y times p of y given x, which is nothing but the expected value of y given x, the integral over dy. So what we end up writing is the expected value of y given x is x. So I just divide by px throughout, 1 by px, assuming px is not equal to 0, assuming support everywhere. There's some, is there a negative sign over here? Yeah, there is. Sorry. There's a negative sign over here because I took the derivative and this is a negative here. So I forgot the negative. Sorry, got it. Put the negative over here. So this is minus sigma squared gradient of px. So px. So now what I can show is, so I know that, what do I know? D log of x or log of fx dx is 1 by fx, the derivative of fx, right? F dash x. The same thing, I will be writing this as, I will write it as the reverse. I can just take this as common. I'll just write this x plus the gradient of x log of px. Clearly, so this is my conditional expectation. So whatever x is given, so it's like a, so what you're doing is the conditional expectation of y, conditional expectation of y, and there's a sigma square also. Sigma square, I forgot the sigma square of y is a gradient step towards the direction that maximizes likelihood. You can interpret it as this way, right? So it's like you start from x and you take a gradient step along sigma square gradient of px, and you get the expected value of y given x. So this is called the Tweedy's formula, and I showed you. So this is like you get the x, you take a gradient step along the likelihood direction, right? So this is going to give me the Tweedy's formula. Now, once I have this formula, let's see diffusion models can be written in a couple of sentences itself. So now we know that xt, I will just copy this. I will just show you how score-based functions can be used in diffusion models. And let us see this from this equation itself. Sorry. So what I'm trying to do is I'll show you how Tweedy's formula can be used in diffusion models to make it give it a score-based formulation. Now, why is score-based formulation important? It will show you that how it can be used effectively for doing conditional generation, right? And also in our future, we'll be seeing EBMs, which will be useful there. So now I can see is the noisy version of the data. So look at this. This is exactly like, what is it like? X is equal to Y plus normal distribution, right? This is normally distributed with particular standard deviation and zero mean. This is your mean of xt. This is my mean of xt, right? Whatever xt I have given x0. Correct. So now let us see how I'm going to write it. So let us consider. So remember the loss function. Loss function we showed was equal to the mu q of xt comma t minus mu theta of xt comma t. Right? So this was the encoding mean of the posterior under the variational distribution Q. This is my decoding mean. We are learning this, right? So now let us look at this expectation. So now again, using the TUD's formula, So here, this is xt for us, and this is x0. So what we want is, what is the expected value of x0 given xt? Right? Or this is one thing that I can do. Or the other thing I can do is, this is not exactly, this is the mean of xt. Is what I'm trying to say. So let's not mix things up. So let us look at, the goal is to find this. This is the goal. But for the time being, let's look at the mean. And then what this, we'll see the mean of this is going to give me the goal. The mean of xt. So plus normal 1 minus this, right? Normal 0, 1 minus alpha t bar into identity, right? Given xt. What is this going to be? Very simple, isn't it? This is going to be, again, xt plus sigma squared is equal to 1 minus alpha t bar into the gradient of xt log p of xt. So now, as soon as I do this, I get the score in the equation, score for the tth time points distribution. So this is so interesting to see. So in all this while I was modeling the joint distribution of p of xt given xt minus 1, all this while we had p of xt given xt plus 1, q of xt given xt minus xt plus 1, comma x0, and so on. But now I have the marginal directly. This is the marginal of noisy distribution. Right? So now, what is this value? So this you can clearly tell me you know this value, right? This value, mu of xt given xt, is already known to us because the image is known to us. Known because x0 would be known, right? Which is the input image. If I know that, so I can just put this mu of xt, which is exactly this value. We already know this value as root of alpha t x0. I'm just putting the exact estimate of the value. The best estimate is the exact estimate. We know the mean of xt already. Best estimate equal to exact estimate, which is, this is mu of xt, which is equal to, again, from this equation, I can write xt plus 1 minus alpha t bar, the score gradient of the score function. So now I'll get an equation at x0 as 1 by root alpha t one minus alpha t bar root alpha t, right? And I'll have gradient of xt log of p of xt, right? This is one of the equations that I'll get. This is from score formulation. Similarly, the noise formulation would also give me another noise formulation. This is equation 1. The noise formulation will give me, see, remember xt was equal to root alpha t plus root over of 1 minus alpha t epsilon. This is equal to x0, sorry. So x0 was equal to xt 1 by root alpha t, right? Minus 1 minus root alpha t bar epsilon, right? So this is what I did. I just removed this to this side and divided by the epsilon t, the alpha t bar. So now if I put equation to, the noise formulation tells me x0 is equal to 1 by root alpha t, xt, sorry, xt minus root over of 1 minus t root alpha t epsilon, right? So now you can clearly compare these equations, compare equation 1 and 2. Equation 1 and 2, and what do you get? You get 1 minus alpha t bar by root alpha t bar is into the score. This is equal to minus of root 1 minus alpha t bar root of alpha t bar epsilon. Clearly, we can cancel these out. Right? And then what you'll end up getting the score, you will have an exact value for the score. And we'll be seeing why is this important. 1 minus alpha t bar into epsilon. So this is my equation 3. So now with this, we have come to this formulation that I know this equation, right? I know this equation. And in my previous session, we showed that. I'll just copy this equation as well. In the previous class, we showed that the QT of xt minus 1, xt and x0 is given by this complicated distribution, which we found the variance for, and I told you to do the algebra for the mean. Right, so this is okay. So let us copy this and I'll just put it over here. Yeah. So in the previous class, what we did is we wanted to show that if you put x0 value in q of xt, we were going to get a denoiser, right? Because we know at the end of the day, xt from x0 is only dependent on a noise term that was added, a stochastic noise term, right? So now let us do that. So, and we know that the loss function over theta is nothing but mu q minus mu theta, right? And this is my mu q. Right, so I want to have a better formulation for mu q in terms of score. The idea is have mu q in terms of score and not noise. Right, we can clearly see that the noise and score are clearly related. As we can see, noise and score are related. right? So what I'll do is I'll just put qt of xt comma t is equal to root alpha t 1 minus alpha t minus 1 bar xt plus root alpha t minus 1 1 minus alpha t, and I'll put the value of xt. What's the value of xt? 1 by root alpha t xt plus 1 minus alpha t bar, and the gradient, right? Log of p of xt. So this is what we showed. The score function and the score function of the 2D's formulation is what is this, as we showed from equation 1, right? I hope it's no root over, sorry. So this is from equation 1. So now once I do that, what I can do is, and I have a division by 1 minus alpha t bar. Since this equation becomes, so I can cancel this term. Okay. What I can do is I can cancel this term out. This is alpha t bar. And I can cancel the bar in the denominator because we have shown that the alpha t bar is the alpha t minus 1 product of, bar of alpha t minus 1 bar into alpha t. We know that, right? Because the bars are the cumulative products. So, okay. So once I do that and pull this out, once I pull this out, I'll have root over of alpha t 1 minus alpha t minus 1. And I will have 1 minus alpha t by root over of alpha t. There's no bar here, sorry. Yeah. Into xt. I have 1 by 1 minus alpha t bar. And I have one more term with respect to the score, which is 1 minus alpha t bar by 1 minus alpha t bar root over of alpha t 1 minus alpha t into gradient of log of pxt with respect to xt, and I can cancel these two terms out. Once I do that, what I get is so I'll multiply this by alpha t and I'll get 1 by alpha t root over 1 minus root alpha t 1, or rather alpha t minus alpha t bar, because I'm multiplying this and I'm opening this bracket out, plus 1 minus alpha t. This gets cancelled. xt plus 1 minus alpha t root alpha t gradient of xt log of p of xt. Right, and then this term also, denominator also gets cancelled with this term. So we get 1 by root alpha t xt plus 1 minus alpha t by root alpha t with the gradient of xt log of p of xt. So this is my equation 4, right? So I have now known, is this correct? Let me just check. Yes, this is correct. So now what I'll say is I know the equation that I know is, I'll just come to conditional generation a bit later. So I'll just put some stars over here and I'll write it at the end. Just write this down over here. 3 stars. Okay, so I'll just write this. So what can you write this as? I have written that mu q of xt comma t from score formulation is given by 1 over root alpha t xt plus 1 minus alpha t by root alpha t, gradient of xt, the score basically, right? So now I will do reparameterization of our model because all we need is another model, the model to estimate mu q, and I'll do that by using mu theta xt comma t, which is 1 by root alpha t. I'll do the same thing. It's just a linear scaling, linear shift and scaling. And I'll say that all I need to do is estimate this. This is the variable, right? The variable is this, so I can just put all the constants in front by reparameterizing, and I'll just say that this is the score function of xt comma t. So now clearly your loss function becomes, your loss L theta becomes the x value of x sampled from px, the t sampled from uniform 1 dot 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 t, the expectation over z, or xt sampled from p of xt or q of xt comma given 0 or xt comma x0. And I will have, if you just subtract these two, what you will end up having is 1 by 2 sigma q squared t into 1 minus alpha t squared by alpha t, right? Into s theta xt comma t minus the gradient of xt log of p of xt. So this is, and we know exactly this is equal to 1 minus root over of 1 minus alpha t into epsilon. So we know the exact formulation. So this is, so what this again becomes similar to, this is exactly like denoising. This is exactly like epsilon theta of xt comma t minus epsilon once you put this value over here. So what I showed here is we show that score matching is same as equivalent to denoising diffusion. Both these diffusions are the same. So once you train one of the models, you'll get the score models for free, is what we indicate, right? With a scaling factor and things like that, that you can use as a hyperparameter and so on. So we showed that the score matching diffusion model is same as the denoising diffusion model. Right. So now once you're able to do that, we can clearly write this as, so we know xt minus 1, but we know this distribution, right? P theta of, so how do we make an inference? Did I write it down? So I wrote down the loss function. This is the loss function. This is also done. So now let us look at the inference. The inference of score models. Inference of score matching. So very easy. This is not a difficult thing. Again, by the same process, xt minus 1, xt given xt is distributed as the normal distribution of xt minus 1 mu theta of xt comma t and sigma q squared t d I, right? This is what it is represented as, right? So now what I can do is I can write this as xt minus 1 is equal to mu theta of xt comma t plus sigma q squared t into epsilon noise. And this I can expand in terms of scores. This can be written as 1 by root alpha t plus 1 minus alpha t by root over of alpha t. This is exactly what we found out. right? So this is my mu theta. If you remember the formulation, so equation 5. So this is exactly my formulation. So 1 minus alpha t by alpha t. Where is this? Sorry. Yeah. Just put this on the right or somewhere. Yeah, and do that. Yeah. So now I can write this as S theta of xt comma t plus sigma q squared t into epsilon. So this is my model again. This is my denoiser. The denoising is again training this unit again with the time embeddings. You give it xt, it predicts the score, and you use the score or the denoised value to generate samples. This is the idea. The idea is, be it the score function or be it the this function of what do you say? Be it the score function or be it the generator function with from the noise terms, both of them have the same formulation because we showed that it's equivalent to training epsilon theta also. Because at the end of the day, you'll be training it over noise itself. You'll be training it to find the noise with some scaling factor here and there. Okay, so now what I'll show is, so that we showed what is inference, how the inference is going to be done. It's done. So now I'll show you why the score function is going to be essential for doing something like a conditional distribution or conditional generation. See, conditional generation, as I have written over here, is given a label y, say for example cat, say cat, do denoising such that it goes towards the cat category. So the thing to think about it, you can think of it this way. So they say this is cat, this is your dog, and say this is normal distribution. And you go towards the normal distribution in the forward process by adding noise. During denoising, you give a label, say cat, and so your denoiser would only denoise along this trajectory and maybe give you a cat over here and not go to the dog's distribution, right? This is your forward process. This is your denoiser or guided denoiser. Where you're trying to guide the distribution towards the cat distribution, the dog distribution, right? So let's now look at look how we will be doing that, but how? But how? This is exactly where the score matching gives you the answer directly. So you may be thinking I'll have to do the entire math that I did for for the diffusion model generation purpose and so on. But since we took all the pain of learning that the score matching is same as the denoising, therefore we can clearly in one step say that we can use denoising to something or score matching somehow here. So that's the idea of showing denoising in terms of conditional guidance using the score-based formulation. So let us look at the score. Let's look at the conditional score. So what's the conditional score? So p theta of x given y, say equal to some y. Could be some small y, right? So y equal to some y. This is the category, say some category. or conditioning value. So once I do that, what I can do is I can write this as, if I write the log over here, I can write this as proportional to or equal to log of y equal to capital, the random variable y equal to y given x by p of y into p of x. As soon as I do this, you'll be telling me, say the tth noisy sample. So, okay. So we are trying to get the tth noisy distribution given the labels. So now if I write this as this, so I can write this. So this y equal to y, this is a constant. This is going to remain the same, right? Because this is a marginal distribution. So I can write this as proportional to log of p of y equal to y given xt plus log of p of xt. So now if you see this, and to bring in this constant, some scaling term, so I will just, to make this equal, I'll use this as a hyperparameter. I'll be telling that this is a hyperparameter term. And we shall be multiplying. So depending on whatever value, what is generating the distribution well, so I will absorb the constant in this form. Okay, so this will give me a hyperparameter to give me a value of this. So this I'll say is log of, and if I take gradient on both sides over xt, p theta of xt given y, this is equal to the gradient of over xt log of p theta of y equal to y given xt plus the gradient of xt log of. So even if if you assume even the real distribution of the data, if we just remove all the thetas, this is going to be the exact value, right? So now you can clearly see this is the score. This is my conditional score. This is, say we will represent this as s theta. So I will write this, I will approximate this as s theta of xt comma y comma t as gamma times the gradient of xt log of p theta. So let us parameterize by theta now, parameterized by theta. By theta, you get y given x plus the score, the unconditional score. So now this is this model. This is the unconditional score. And this is my classifier. 16 again. So what it does is it takes in xt and tells the class of y. So now during inference, what you end up doing is, so this is essentially building this model separately. This model classifier, and this is the classifier that predicts class from noisy data. So you generate both of these, you train both of these models, and during inference, what I do is, during inference, your xt minus 1 is given by root over of alpha t xt plus 1 over alpha t root over of alpha t s theta of x comma y comma t sigma square q free epsilon. So now this is just changing this to two terms, right? So your score just changed to score of xyt because it's a conditional generation, but that is essentially doing conditional inference. Is doing 1 minus alpha t root alpha t. This is s theta of xt, which is the same classifier, same denoising model, same denoiser denoiser plus the gradient of over xt log of p of y given xt plus sigma qt squared epsilon. So which is telling me that this is a guidance term. Guidance through classifier. Hence it is called classifier guidance. Classifier guided diffusion. Diffusion model. Right? So which means that you have this s theta term. Often this s theta xt comma t comma y is y and t are fed to it. Although the initial formulation does not have it, but often for better performance, y is also fed to it. And you get your xt and y is fed to it, and you get the score function xt, t, and y, and you get s theta. And you take this noise and pass it through a classifier which predicts y. And use these two to make your generation or your inference that you have. You just remove the score or add the score because this at the end of the day, the noise is on zero mean. Minus noise and plus noise are both the same. So you remove the score or the noise and add the classifier guidance towards the value as the gradient. So it's like this is if you're adding this, which what does this mean? If you want an intuition, the gradient of xt log p theta of y given xt. If you're adding this, it maximizes the probability of prediction of class y, which means I am generating that class itself. It's just gradient ascent. Look at it as like gradient ascent. So I am improving the features such that the probability of a particular class is enhanced. Okay. So now this is why we did the score-based formulation, and this is the conditional diffusion model that we have trained. We'll be seeing this formulation in the implemented in code in the next class. And with that, we have ended what is diffusion models, what are diffusion models. And we'll be ending today's session with this idea of conditional generation. How could you do it in VAEs? Right? In VAEs, you can do it very simply. You can make this graphical structure, say Z and Y, both explain your data X, and say your Z also explains Y. So this is your VAE, graphical structure of the VAE. Right? So now, the elbow, the L theta phi, if you recall, is given by the log of p theta of x comma y comma z, the joint distribution, and q phi of, you can take any variational distribution. So what we will choose is z given x and y. Because both are known to us, what is the particular latent that I'll get from x and y is what I'll choose. Given x and y, what is the particular latent I have? So say this is the variational distribution I choose. So okay, and then I can expand this term as q log of p theta of x given y comma z, right? Into p of y comma z, which can be again written as, so since from this graph structure, given z, y is independent of x. So you can write this y given z into p of z, right? By q phi of z given x comma y. So now I will group the terms. I can write this as the z sampled from q phi of x, q phi of z given x comma y, log p theta of x given y and z, plus I will take this term and this term as I did last time, plus the expected value of Q log of T of Y given Z, right? Minus the expected value of over Q log Q phi by TZ, which becomes the expected value of over Q log P theta of X given Y comma Z, plus the expected value of the classifier. The same way, I'm getting a classifier here as well. Z minus the DKL divergence between Q phi of Z given X comma Y and T of Z. Same generation per procedure. We have the same generation procedure, but how do you generate it? You make it fixed to the normal 0, 1 distribution, and we have this model as the VAE as you pass X comma Y to the VAE. This is the encoder Q phi. This will give me Z, right? Again, you pass the same Y back to the decoder, and this decoder is going to give me P theta is going to give me X hat. During inference, and you can use this Z to pass it through a classifier. That's what we get the term, this term from, to predict your Y hat classifier. So this during inference, sample Z from normal 0, 1, select choice of label, and then X generated is just P theta of X given Y comma Z, which is some model M theta of Y comma Z. Right, so this will be say modeled by M theta, and this will just decode the value of from the latent and the data. Okay, so with that we come to the end of conditional VAEs, conditional diffusion models, score-based models, and diffusion models in general. We'll see the how we actually implement diffusion models in reality in the next session. So if you have any questions, please put it down in the chat. We'll be referring to it and we'll be solving them in the doubt clearing sessions. Right? So with that, I'll stop recording for today's session and we'll see you in the next class.